Okay, we're live. So
Oh,
yeah,
cool.
Perfect.
apologies for the delay, everyone. That was entirely my fault. I got a bit way late at an event. Got pushed back an hour, and fortunately they let me know. But now we're here, and we have Ruilong, and we have Janusz and Mr. Nerf as well. So yeah, welcome back to episode 2 of the Radiant Field live stream / podcast / fun hangout time. So yeah, welcome everyone. We have our guest Ruilong Li, who, if you've ever used Nerfstudio at any point in your life, you have directly benefited from Ruilong's work. And yeah, I'm very excited to be here with both Ruilong and Janusz to talk to you all today.
Yeah, I'm also very happy to have Ruilong tonight on our podcast. I'm a big and huge fan of your work. It's just incredible what you guys pulled out, and you keep on pushing. It's so much fun to see the project growing and the community is as well growing. And every time I look at the pull requests, I'm pretty excited because there's like every week a new research paper coming up, which is opening a pull request, and you can basically live try all the new features which were last week on archive. So it's so exciting to have you here.
Yeah, no, without exaggeration, bilateral processing was just shown at SIGGRAPH. Then like 1 week later, it's already merged into Nerfstudio. So the rate's been like incredible.
Yeah, you guys are doing so good on keep tracking of the new things, especially including like the development in Gsplat. I'm so grateful on that, and also I'm really happy to be here to share our development and the stories behind it. And personally, I also really like all those tweets you have, all those like article Michael wrote on the radiusfield.com, because that's becoming like one of the major resources for me to get know of the new research. And actually, like the multi GPU kind of Gaussian stuff that we are going to talk about. I learned that from your posts, and I started to think, okay, this is cool, and I need to integrate this. And now we have it in Gsplat.
Right, the Grendel from NYU, that one.
Yeah, exactly.
Yeah, it's pretty crazy to just see the rate of the technology progression. But no, we definitely want to like talk about you as well, and kind of like go through like how did you just end up in the world that has become Nerfstudio, and like how did you become interested in reconstruction?
Yeah. I guess in general, my I had a kind of a long research journey already as a PhD student. So I did like a 3 years master back in China, and it's like kind of research based master. So also like a 2 year research assistant kind of a role in USC before I joined in UC Berkeley, and now I'm like at the 4th year of a PhD program in UC Berkeley. So it's quite a long journey for me. And I started doing research not in 3D completely. It's just about like 2D detection and like some key points, like analysis for human. That's my like kind of initial research project. But like from that initial project, I started to feel like detecting key points for humans, for example, is just not gonna be solved completely in via 2D approach. Like seeing humans in 2D image is always just a slice of the 3D world. Is always like it's super hard to like distinguish the different humans on the 2D image. But when you lift it back to 3D, is very easy to distinguish them. So I'm starting to think about questions like that, and then this motivates me to kind of apply for a PhD program, and in the field of intersection of graphics and vision, and start to do things like reconstruction and basically trying to understand the 3D from images, and doing some analysis based on that in 3D. So yeah, that's basically how I entered the field of 3D reconstruction. My kind of first 3D reconstruction project was about reconstructing human from a single image, and we kind of put a lot of engineering efforts into it to make it real time and demonstrate it in the real time live of SIGGRAPH. in 2000 and I don't remember which year, but like 3-4 years ago, and unfortunately got a best demo award out of like a SIGGRAPH real-time lab.
Wow.
So yeah, it was pretty exciting and interesting to me to see those like 3D model got extracted from just a single image of human captured just using a like logic camera, like really cheap camera, $5 camera, and it's all in real time. So that was really cool to me to see this happen, and that was like back in 2022 or 21 before the Nerf came out, and basically right after that Nerf came out, and then I saw this paper. It's super cool, and the fidelity of that is just another level. So then I basically started to look into that and learn the graphics knowledge about like volume rendering, all those equations, and see how actually the 3D is kind of emerged from those images in a kind of principal way. So that's about Nerf, and I basically joined the UC Berkeley at the same time, starting to collaborate with the talents here on doing research around radiance field. Like one aspect is about accelerating it, because basically I was also quite a fan of accelerating things, make things fast. And another side of research direction is to kind of apply nerves to dynamic objects, like human, for example, or some in general dynamic objects. So that's how I get in touch with nerve in my research journey. And apparently, after like the nerve like explode for like 2 years, Gaussian splatting came out, and it just makes everything crazily fast. Because I was also kind of putting quite a few efforts on accelerating nerves, and 3D Gaussians is just another kind of explosion to me, because it's basically bring this like acceleration to another level. And then basically I started to do research on 3D Gaussian. And in the meantime, I mean, doing research needs some tools or some code base that is handy to use. And in the meantime of doing research, we find out is actually the research field is evolving so fast that there isn't really handy toolbox or code base that we can develop upon. So that's why the Nerfstudio, we initialized the efforts of Nerfstudio in the beginning, and after that, is Gsplat is basically the same motivation. We want to incorporate those best technology in one place that we can build upon the best toolbox of doing this task from this like integration of all the new technologies. So yeah, that's basically my journey. I also kind of interned in a couple places like Google, Facebook, Reality Lab, and NVIDIA. So all those experiments in industry kind of helps me to grow my coding skills and the skills to management this kind of projects, like open source projects. So those are also pretty critical kind of experiments to me, experience to me, and which brings me here. So yeah, that's basically introduction about me, a bit long, but I guess it's like the full story of me here. Yeah,
that's very interesting. You were part of the whole progression, starting even before nerves and then transition to Gaussian splatting. Maybe you can explain a little bit where you see nerves shine over Gaussians and vice versa. So where are the advantages of one technology over the other for you, or from your perspective?
Yeah, totally. So I guess Nerf or Gaussian, they are, first of all, they share a pretty common kind of basis, which is the volume rendering or we call another way to call it is the alpha compositing technology. So the formulation of them, the underlying formulation of them are basically the same. And the way to actually implement them is totally different, which is in NERF is about casting array, and you create samples along the array. But in Gaussians is about treating Gaussian as primitives and rasterize them into image plan. So in the graphics literature, this kind of remarching or retracing versus the rasterization is basically two type of implementation of a rendering out an object or a scene. So from that perspective, the difference of remarching and the rasterization is just about like implementation difference. And as you can see in the latest papers for the 3D Gaussian, there are also ways to just shoot a cast array and trace through the Gaussians and render it. So, as the Gaussians are just primitives, casting array, the implementation of going through the recasting is going to be harder and slower than rasterization, but that's the natural, that comes from the nature of this ways of implementing it. And other than that, it's about the representation. So when the first NERF came out, is using the MLP to represent the scene, using the MLP to kind of memorize what's in the scene. And then kind of a few voxel-based explicit representation came out, like plan oxel or triplan, represent the scene in a different way, but still using the neural radiance kind of formulation. Actually, I want to point out, like for the plan oxel, it's not a neural anymore; it's just a radiance field. And in that perspective, if you go from plan oxel to 3D Gaussian, they are actually more similar because they are all explicit structure. They are not neural anymore. They all based on the volume rendering equation, and it's just the difference is just representing the 3D in the voxel versus representing the 3D in the 3D a set of 3D with a set of 3D Gaussians. So from that perspective, is actually not too much of difference. It's just a matter of what kind of representation you use to represent the scene. So that's like kind of on the research side to compare this 3D Gaussian NERFs. But on the implementation side, I guess one thing is the rasterization versus the remarching that I talk about. And the other thing is that the rasterization enables, because it's explicit, it enables really crazy CUDA programming to make it fast. Whenever we introduce some MLP in your model, it's very hard, almost impossible to kind of put it in a highly customized CUDA kernel. So highly customized CUDA kernel, like explicit structure, are really friendly to CUDA programming. So that brings basically the Gaussian splatting to another level, especially when we talk about the crazy rendering speed of Gaussian splatting. It's actually 90% benefit from the CUDA programming, because we have a Python version, and if you use that Python, we had a Python version in Gsplat, and if you use that purely Python version to render out the Gaussian splatting, is still fairly slow, like NERF speed basically. So yeah, that's I think the difference and the connections between these two type of research. And also because they share the fundamentally they share the same kind of mathematical formulation of volume rendering. The techniques can be easily, like many techniques can be easily transferred from one to the other. And you might have already seen quite a few papers basically doing the same task by replacing the NERF to Gaussians. But in terms of like quality, like somewhat like one type of question is which way can give us the best quality. I would say because their fundamental is the same. The difference is just about the representation itself. So they might have a similar kind of limitations, especially on the performance side. They might have the similar kind of top like top limit. But in terms of now, nerves have been like developed for like 2-3 years. Like Gaussian only like for 1 year. So as this moment, still nerves, like the best nerves have like best quality. Basically, zip nerve type of research is still shining out in terms of quality. And 3D Gaussian, I would say, has a long way to go, but I think in the end it will definitely reach the quality that what Nerf has. Right, and also because the rasterization nature of 3D Gaussian, there are some limitation in 3D Gaussian that Nerf didn't have, but that comes from the rasterization nature, which is, for example, the perspective projection is kind of hard encoded in the rasterization process, and whenever you have a different camera, like a fisheye camera, you have to kind of write another projection kind of function to handle the rasterization process. But for Nerf, is ray based. The minimal element is ray, and all the cameras can be handled. Different type of cameras can be handled rather easily by just converting them into rays, and you can just render out the image based on the rays. That's kind of also another difference between the two. Yeah, I guess that's basically all in my head at the moment. And for the details, I guess I can keep going, but I think high levelly that's all the
Yeah, it could be a very long conversation by itself. Just we'd be here for several hours. One of the things I wanted to talk to you about is the destination of Berkeley, which has become like this like hub of like radiance field research. So having Matt, Ben, and Pratul coming out with the original Nerf paper, and then having people like yourself and Alex Yu, who is the CTO of Luma and the co-founder of Luma AI. I'm kind of curious. Like, so it was you, Matt Tansika, and Professor Kanazawa that kind of were on the NERFAC paper. And is that kind of like how you got into the Nerfstudio atmosphere? Like, how did that all come together?
Right, that's a great question. I guess several kind of factors in this story. One is like in UC Berkeley, like there are just so many talents, like Alex, Matt, and all others. They are just so good at both programming and designing, and also like the mathematical side. And just it's a very talented group of people to work with. And another thing about UC Berkeley, kind of which is a little bit special about UC Berkeley, is that the grad school in UC Berkeley has this very collaborative atmosphere. People here like to talk with each other and get to know what each other is doing, and like find out opportunities to collaborate with each other. So that's kind of a little bit special among all the grad schools in US, and you definitely know that the first Nerf paper is co-authored by 3 kind of PhD students here. And that's actually pretty rare if you look at all the other papers. Like 3 kind of senior PhD co-author a single paper is not a common situation. But here, also Nerfstudio, you see like 3 co-author first paper, and also a bunch of kind of contributors, including a couple PhDs, how was this project. So in UC Berkeley, we really like to collaborate with each other. And I mean, definitely 3 PhD, what can come out of like 3 senior PhDs, if they are all good PhDs, they could deliver something much more much cooler and impactful than just a single PhD, what the single PhD can deliver. So from that perspective, I'm not too surprised that the papers or the projects came out of UC Berkeley are all or most of them are pretty strong papers or projects, because we just like to work with each other and learn from each other. Actually, that also benefits me a lot because I not originally come from 3D, and I learn a lot from Matt, from Alex, from other people here by just joining those projects and helping them. And especially like Nerfstudio, we build a community in this Nerf literature, and all those people coming in to share the knowledge of them and contribute their latest research to it. For us, I mean, we manage the toolbox, and we try to merge their latest research. And in that process, we actually learned a lot, like on the actually programming level, which has all the intricate details behind the algorithm. So that's about the kind of the specialty about UC Berkeley. And also,
I think maybe one question, because I think you guys are the melting pot in a radiance field world. And what is very interesting to me, because you are spanning practice and research quite well. So especially Gsplat is maybe a research project, but it's also highly relevant to practice. Many companies are hopping, I think. Yeah, he's back. Many companies are using Gsplat for their products already. And I also saw your latest paper, which is called Nerf XL. And I think Michael posted it that Jansen called it one of the most important papers. So maybe you can, so you can maybe elaborate a little bit why he called it that way.
Yeah, like FEDB is a project I got involved in when I was interning with NVIDIA. And that one was a pretty fundamental toolbox for 3D spatial intelligence. That's how we call it. And it's basically provide a structure for any 3D type of data that you can use to kind of store the data, and also like interpret the data, for example, remarching through the 3D kind of representation. And so that means, and also all of this are differentiable in FVDB. The FVDB stands for feature VDB. It come from OpenVDB and build all those differentiable ability on top of it. And in terms of Nerf XL, it's actually using the FVDB as an acceleration structure. And also because the FVDB is built in a way that is super memory efficient, that basically using the VDB structure to compress all the spatial data, which makes it memory efficient. So in a Nerf XL, we trying to scale up the Nerf reconstruction to a crazy large scale. We can spread it into multiple GPUs, but we also benefit from some kind of spatial structure that can make it memory efficient and can accelerate the remarching in this 3D structure. So in Nerf XL, we use FVDB as the spatial kind of accelerator or the spatial structure of Nerfs. And we also have the mathematical equation and the algorithm on how to distribute the Nerfs across multiple GPUs. And together, we basically build a system that is pretty robust to the scale of the Nerf reconstruction. And we tried it like on up to 64 GPUs because that's my limit quota when I'm interning with NVIDIA. but it has no reason that it can't go more, because 4064 GPUs is already cross nodes. And so basically it has the ability, because it can scale up super well. Like we showed the scaling rules that emerge from just using more GPUs. We believe, and we have a couple demos showing that it can basically support this kind of a few applications like autonomous driving or the CT scanning, like using drone footage. Those kind of applications those applications need details to be reconstructed while the scale of the data is huge. And the NerfXL is basically there to support that. And in terms of FVDB that Jensen was promoting, it has actually more applications than NerfXL. It can support, it's like more of a lower level kind of support for NerfXL, and it can also support other things like 3D. There is a paper doing 3D generation using voxels, which also benefits from FVDB, and also other simulation kind of tasks also benefit compact and efficient 3D structure, which is differentiable. So that's what FVDB is, and also the NerfXL projects.
So maybe one technical question, because I was wondering the large scale city, the 25 square kilometers one, how long did it take to render it?
You mean render or train?
Yeah, to train it, and then.
Yeah, great question. So that one, I think we trained the biggest scale was on 64 GPUs, and it was trained for like 10 hours or a little bit more than 10 hours. But I think we didn't really optimize for the training speed for it.
Mm-hmm.
And it was, I think it might be a little bit overkilling on the number of iterations that we set to train it. Because I mean, we just set it to whatever and trying to get the best quality out of it. But the results that we posted, I believe, was trained for like 10 or a little bit more than 10 hours on 64 GPUs.
And we have a question here. What kind of GPUs did you use for training?
Oh, I think it's V100.
Okay.
Yeah.
So I kind of want to talk a bit about like the development process from for Gsplat 1.0, because even just to re-implement or to kind of build a new version of Gaussian splatting for Nerfstudio, I'm sure it was like a massive endeavor, and the changes and updates that you were able to put forth in 1.0 were also just like a huge step forwards too. So yeah, I'd love to be able to talk about like that development process.
Oh yeah, totally. So I guess for the Gsplat, there is a story behind it, which is like it's initialized by Vicky. Vicky was also a PhD student here. She just graduated this summer, and she was actually using this project to practice her CUDA skills and trying to understand what is happening in the Gaussian splatting technology. And so this repo was initially not called Gsplat, but called 3D Gaussian exercise. So it's basically an exercise repo that Vicky created. She first read the paper, derive all the mass, like write out all the mass behind it. And she also had an archive document about all the mass, like that she created, like she learned and rewrite the mass. And then she created this exercise repo to kind of code out the Gaussian splatting based on the mass that she organized. and also trying to get familiar with CUDA skills. And this is actually her first CUDA project, and it turns out super well. That the Nerfstudio projects can kind of just embrace it and use it as a backend to support Gaussian splatting in Nerfstudio. So that's how it initially emerged. And so at that time, I was working on NerfXL in NVIDIA and almost finished it and wrap it up and looking for a next project. And then we realized, okay, so the multi-GPU distribution technology can actually be applied to not only Nerf, but also Gaussian. And so I started to kind of look into Gaussian, would like to try to use Gaussian for a large-scale kind of reconstruction, to support the large-scale reconstruction using Gaussian. So that's how I got into the picture of the Gsplat project. Okay, our lab has this project that is working pretty well, and it can be, it has like commercial kind of free license, and that's also kind of benefit me doing an internship at NVIDIA. So yeah, so I start to look into this code base that we have and trying to support large scale data using that code base. And we turned out, so I turned out identify a couple of places in the code base that can be improved in terms of efficiency and the memory, like speed and memory efficiency, because for large scale reconstruction, of course, I can distribute it to multi GPUs, but if the code base itself is efficient enough and memory friendly, I can also benefit from that. So my first kind of goal is to kind of push the limit of this Gsplat repo through some serious engineering to reduce the memory footprint of it and to like make it as fast as possible. And that's how I kind of introduced like Gsplat 1.0 after like a month of efforts of doing this engineering, rewriting, cleanup, and some improvements. And basically the motivation behind it to support large-scale reconstruction. So that's how like batch size was supporting was introduced, and some kind of memory reduction and speed up was achieved. And also some like actually there is some research idea behind it, which is like the for the Gaussian splatting, when you train it in a really large scale content, every iteration that you optimize, you actually only optimize a local area of the entire Gaussian splatting, of the entire Gaussians set of Gaussians. So that means your gradient of training this all the Gaussians is fairly sparse. Only a couple of Gaussians get the gradients when the scene is crazy large. And that's basically the way that we speed up and reduce the memory, basically to take advantage of this kind of sparseness of the Gaussian training, that only a couple of them has the gradients. And we don't need to update others, and we don't need to calculate others. So that's also the way that we support really large scale rendering, that we just pre-identify some Gaussians that is too far from your camera and you are not going to see it anyway. So we just skip rendering them. So that's kind of a small kind of idea behind it, but it brings a huge difference after we implement it. So yeah, and after that, then the Gsplat 1.0 came out. People seems to be quite interested about it, and the wheels kind of starts rolling. PR starts to coming in, and people are starting to kind of request more features, and sometimes they contribute more features on top of it. So up to this moment, we have like some new features comparing to 1.0. One of them is like the multi-GPU support. So there was a paper came out, the G. Randall paper. That one was pretty good on doing a multi-GPU like distributed training. So we incorporate that paper into Gsplat. and also MIP splatting, which is like the best student paper of CVPR 2024. We have a PR for it, and have already support like part of it. It has like 2D filter, 3D filter. We support like 2D filter, but the 3D filter is currently living in the PR. And the 2D Gaussian, because we also realize like 2D Gaussian is not quite different than 3D Gaussian. It has quite a couple of things can be shared between them. So we also were trying to incorporate 2D Gaussians into Gsplat. And I think the PR is almost ready, and it might going to be merged in within a couple of weeks. And also a few other papers, some of them are doing compression. We recently like merged in a compression technology called self-organizing Gaussians. There is a paper recently released, and we kind of did a few modification, some slight modification on top of it, and combine it with the other paper that's living in the Gsplat called Monte Carlo something.
Markov chain.
Yeah. We call it MCMC. So that's giving that is approach that gives you a kind of a better quality with less Gaussians after training. So combining with this MCMC approach with this compression technology that we introduced, and which can be easily combined in Gsplat, because each of them are kind of modularized pretty good. And combining these two, we kind of achieved like the top one performance on one of the leaderboards for 3D Gaussian compression. And all of these were living in a PR, but we recently merged. So people can find out them, just go through the Git commit history of Gsplat.
Yeah.
And
It's been pretty crazy too to like set the context of the compression. Just when Gaussian filing first came out, like a little bit over a year ago, the original INRIA method, the resulting PLY files would be approaching like a gigabyte each, and now it's like with this new update, it looks like it's roughly like 8 megabytes roughly for each 500K Gaussians in the scene. And it's just like crazy to see that the magnitude of compression in this period of time.
Yeah, exactly. Also the algorithm is super simple. Actually, I can just describe in a single sentence, which is to convert Gaussians into an image representation and use the image compression technique to give you the compression rate. And this works super well, and you don't need to do any training tricks. No modification in training, just a post-processing compression, and that just works super well to give you like 20 times or more like compression rate out of box. So that paper was super good. I do recommend people to read through the paper.
There's also someone was asking about the like UI, like automatic 1111, and there is the Gradio instance, right? Which I think I can't remember if he's also a student at Berkeley or not, but someone added a Gradio instance, which does make it really easy to like set all the flags and such for Nerfstudio. This way, you can kind of just like toggle what you want on and off and start your training.
Yeah. There was a visiting student in UC Berkeley that working in the Nerfstudio project, create this Gradio for Nerfstudio, and I think it's also open source now and is ready for people to use. It's pretty handy to set out those flags. So yeah, that's supported like a month ago, I think, released at that time. Yeah.
There's also much more, right? I'm always fascinated by the pull requests. So there's also bilateral guidance, which improves the quality, especially if you have different appearances on the images, which is pretty cool. And there's also one guy on the Nerfstudio Discord who loves to compare all the renderings with the newest techniques. And there you can basically see what's coming and how the renderings are improving. It's phenomenal. But there's also, I saw like something like spotless Gaussians. So that's a lot.
Yeah. So there's a lot of techniques are kind of using Gsplat and the Nerfstudio, and I mean also some techniques are coming in, like the bilateral grade is actually a pretty good approach to deal with the appearance issues, like the exposure and white balance issues, and is actually also a general approach across Gaussian and NURBS. So the paper came out doing experiments on NURBS, but apparently it can apply to Gaussians. It's not tied to the representation itself. So we basically incorporate that into Nerfstudio, and there is also a PR living in the Gsplat about it, which is working pretty well on the cases that you have severe kind of exposure and white balance issue in your data, and you want to kind of cancel out those effects when you do the reconstruction. Actually an alternative approach to that is using the kind of Nerf in the wild paper approach. So Nerfstudio recently also released a splat factor W, which basically implement the Nerf in the W approach into a splat factor for the Gaussian splatting. That one can also help you to remove the or compensate the white balance and appearance issue, and it has actually more functionalities because that in splat factor W also supports like removing the dynamic objects in your data, and also like take into account the background can be kind of modeling in a different way, more a simpler way in that paper. So that was also coming from the like one of the undergrad or visiting students in Nerfstudio team, because we do engineerings in Nerfstudio, but we also trying to solve problems in Nerfstudio. And whenever some solution came out, it naturally forms into a paper. Exactly this one that Michael was showing. And you can also interpolate across different kind of appearance, which is very cool.
That's very cool. Yeah. Can you tell maybe something about the agenda of Gsplat? So where are you guys heading, and how are you planning what you want to incorporate?
Right. So I guess currently there are a couple of things living in the PR that is there are pretty useful techniques that we are trying to merge. And other than that, I think long-term wise, I'm trying to find a unified way to kind of represent or to integrate those different techniques, because 3D Gaussian, we know it's based on rasterization and is based on the it's using like highly customized perspective projection. And when you change the camera model, and you have to customize another type of projection from 3D to 2D. And those things are currently not supported in Gsplat. And the reason is that when we initially kind of build Gsplat, it only considered perspective projection, but there is some way to there are ways to make it also compatible with other camera model. I guess that's kind of one of the longer goal, but that requires some reformatting of the code to kind of make things modularized. Because we do see a lot of benefits from just making everything modularized. That means we can stack one technology on top of the other to get better results. And so camera model, that's one thing. And the other thing is, like for the Gaussian splatting, we are currently supporting like batched rendering. Let's give it a scene that we render multi-image at in one go. But there are also, I also see requests on batching over the scenes, which means that you probably want to render couple of scenes at the same time in one go, and especially in the case of foundation model learning, for example. You want to train a model that's in whatever kind of application that using 3D Gaussian as a representation, and you want to kind of do this batch training. That's where you need like batchify these over multiple scenes. So we do see some needs on that direction. That's something we could support, and it's a bit in the long run. And also, like accelerating and speeding it up is always something that we are actively looking into. So there is a paper recently coming out called Taming 3D Gaussian, having quite some good acceleration technologies. And I also got in touch with the author of the paper, and I think the integration of that is also on the way to further accelerate and make the overall rendering faster. There are some technologies like this acceleration is super general across all the variations of Gaussians, and those technologies are the things that we are looking for, that we want to incorporate them so that we can benefit most of the researchers doing Gaussians in this field.
Yeah, I was very excited about, sorry, Michael, about the tabbing paper, because it's even faster than Gsplat, right? And I was wondering, okay, what if you combine both techniques? Because they have some tricks in the backward pass where you just save computation by not touching every Gaussian and every thread, right? And it's so fast already, and I think if you combine both approaches, it's gonna be a speed up by 2 times or 3 times. I don't know.
Yeah, exactly. I mean, apparently we are not the best coder. There are apparently other coders out there that are just better than us. So we are trying to incorporate those best technologies into Gsplat, including the best implementation to Gsplats. And also, I think we also trying to port some of the new kind of technologies from Gsplat to Nerfstudio when it's becoming mature enough and modularized enough in Gsplat. For example, there is just a PR kind of open today in Nerfstudio that we're trying to port the strategy, which is the densification strategy class defined in Gsplat into Nerfstudio, so that Nerfstudio can easily toggle between the default densification strategy from original 3D Gaussian paper and the Monte Carlo paper, and also another paper called ABS Grid. So we basically trying to figure out what's the best way to modularize those latest papers in Gsplat in a pretty aggressive way, that we first allow those PRs to come in, and then we figure out, okay, the common ground between those approaches and merge them and modularize them. Once it's becoming mature enough, we are trying to port it to Nerfstudio so that the bigger community can benefit from them. But we are basically pretty cautious about importing things into Nerfstudio, because we don't want to revert things back in Nerfstudio, considering the amount of users is using it. So yeah, that's basically the long-term kind of plan here.
My vote is still always the stop the pop paper to be implemented. So if anyone who's listening is so inclined to take out a PR for that, I feel like it would dramatically help increase the fidelity or close the gap between splats and nerfs for their reconstruction fidelity.
Yeah,
So-
totally. Yeah, I would super supportive for that, for having a stop the pop support in Gsplat. Yeah.
And kind of along those lines, then. So say you're at home and you're listening to this right now, and you want to like go out and take a PR. Like what would be most helpful, for you as the maintainer of or as one of the maintainers of Nerfstudio when going through this?
Yeah, so for Nerfstudio, it's a rather big code base. So I guess I would suggest you to first play with Nerfstudio a bit on reconstruct a couple of videos or image sets to get some results first, to get familiar with the code base and how it's being used. And also there is a document on the Nerfstudio website about the instructions on how to contribute. And so I guess there are typically two types of contribution. One is that someone creates a paper and using Nerfstudio and wants to introduce their technologies back, contribute back to Nerfstudio. And the other type is like bugs fixing, I guess. For bugs fixing is quite easy. I guess it's just a couple lines and you do some formatting following this kind of tutorial. And for introducing new features, like if it's a big feature, it's going to touch quite a few files. I would suggest you to contact with us either Brent, Justin, or me, like either on Discord or sending us an email to maybe first chat with us, because introducing new features are always useful for users, but it also have this it also introduce some burdens for the maintainers to kind of maintain it. So there is a story about Nerfstudio behind it. When at the old time, like a year ago, like when we introduced so many papers into Nerfstudio, and are really this repo becomes really hard to maintain. We had a kind of major kind of reformat of the paper and had to move out a couple of papers that we were supported in Nerfstudio into their independent repos. And that's how we kind of also putting up a document on Nerfstudio about the guidance of how you could having your own repo set up in a really easy way, and using Nerfstudio as a dependence to support your own, to kind of share your own research. Yeah, and for I guess we also have a, so the Nerfstudio also has a bi-weekly meeting that the maintainers in UC Berkeley would just meet and talk about the development and the maintenance of this. And if there are some major features coming in, we'll discuss and we'll see if it's fits in and is easy to maintain. So I guess if the research is pretty general, can support quite a wide range of nerve variations or Gaussian variations. Those research we are pretty happy to merge in. If is highly customized, then probably it's best to host following our kind of documents on how to host it in your own repo and still benefit the latest and greatest from their student.
Oh, very cool. I wonder how much time you devote to this project, because it seems you put a lot of work into it. And how do you share your time between your work you are doing for your PhD thesis and also between Gsplat, the Nerfstudio project?
Yeah, I guess I'm just interested in doing this kind of engineering things. So I see it as a fun stuff to do in my free time. And research is like another thing that I have to do for graduation, or to kind of like publishing papers is something that I need to do. But this is something like the managing and the coding things for Gsplat for Nerfstudio is just that it doesn't actually take too much of my work time. Probably take most of my free time. Yeah.
So you're gonna contribute also when you are done with your thesis?
I think so. I think maybe so yeah, I'm by the way looking for jobs right now. I've been graduating in after this semester, and so after this I think I'll still maintain this project until the day that people find it's not useful anymore. Some like new technologies came out, maybe. But yeah, if people are still using it, I'm happy to kind of keep maintaining it.
So yeah, I believe you have like many inquiries if you can work for companies. But anyway, what do you project into the future? So how do you see the technology evolving, and what will be the next big thing, or where will it be used?
Right. So from the research project perspective, I think 3D Gaussian and nerves are. I mean, 3D Gaussian still has some way to go to match the quality of nerves, definitely. But other than that, I think there is a fundamental limitation for both nerve and Gaussians, which is like basically it can only reconstruct the object that is having a nice multi-view coverage in your data. For the image or for the object or the region that is not covered that well or even not being seen at all in the training data, neither nerve or Gaussian would give you a decent reconstruction there. And actually having a complete multi-view capture in real life is becoming harder and harder when we trying to scale things up. Especially for the autonomous driving, the car driving on the street gives you a camera, but that camera only allows you to reconstruct the space that having a kind of good looking rendering from the regions that is near the original kind of camera capture trajectory. So if you want to fully reconstruct the space, you need like enormous amount of captures, like covering all the view angles and at all the locations. That's just too unrealistic. So some heuristics, some generation technologies or some like, for example, diffusion stuffs would definitely be useful here because we are always gonna see holes or imperfect kind of reconstruction that is caused by the data, which is so expensive to capture. And that's where we need some hallucination kind of technology to come in to help with nerve and Gaussians to do the reconstruction and reduce the burden of captures. That's what I see as a big direction on the research side to go. And it's also quite trending now. Yeah.
So Nerfstudio does have Generfacto as a method, which has kind of sat on the sides for a little bit. So do you see new life potentially coming into the generative side for Nerfstudio down the road?
Yeah, I think it's mostly these generative priors can be improved, and it's been improving a lot during the past months. Like for example, I see this like Cat 3D paper from Google, which is super cool by just having a nicely working multi-view diffusion model. And that model just basically boosts the quality of the nerve reconstruction to another level with the requirements only like 3 views of captures. And that thing can still be improved for sure with the like increasing amount of data that we have at the moment. And so the diffusion model or the prior knowledge that we know about the world, including those foundation video models and like those language models that everybody is developing at the moment can definitely be improved over time. And that's the thing that we are going to need to help with the reconstruction as well. And especially like not only like in the field wheel scenario, but also like for the dynamic scenario, like dynamic is always a problem for the reconstruction, because for dynamic, you just won't be able to capture all the viewpoints at all the time steps. And it's gonna be a yield post problem that we need some prior knowledge to help with the reconstruction. And the prior knowledge can be better and better, and it's gonna be much and much more useful for nerfs and Gaussians to get a realistic reconstruction. And in the meantime, you might be able to get some like interesting kind of generation results out of it, because for example, for the dynamic reconstruction and for the regions that you never see before, you can have a generation model to kind of create different variations of it, and then it can, for example, in the simulation kind of tasks, that if the capture never see this region can have multiple possibilities, basically like having a car there, or having a person there, have a building there. So in a simulator, like when you want to improve your self-driving cars, you want to simulate all the scenarios, and you want to have some like generator to create this scene that respect your captures, as well as, and in the meantime also be able to create your multiple variations of the scene following the distribution of the real world. So that's something can always be improved, I believe, and can be more and more useful once it's getting mature.
Yeah, I think the dynamic part is really hard, but awesome if you have multi-view capture, like this big setups in some studios, and you see the capture and you can just rotate your camera while you see the scene in action. Basically, that's impressive. And for me, it's kind of the future of movies. And but I also see that it's really hard to solve, because every time you see the monocular captures, you see when you pan the camera a little bit, the quality breaks down. So
yeah, exactly. Yeah.
Awesome. Well, I think we're pretty much at time already. Like we said, we could probably talk about this for like hours upon hours. There's so much to go through, and Ruilong has been like so centrally involved in just the progression of this technology. So thank you again for making the time, Ruilong, to have this conversation with us. And is there anything I guess before we end as well, I want to like ask for your suggestion for like new researchers who are like entering this field, or even considering going down and pursuing this. So what are your thoughts?
Oh yeah, I guess the research is evolving so fast, and sometimes I feel like even for me it's pretty hard to like following the new research, but also I guess there is also an important factor, that is whenever we want to do research in some fields, we want to kind of understand this field deeply, or understand it in a more comprehensive way. And so my kind of experience and my philosophy of doing research is that I want to first understand the technology completely before I start to kind of improving it. And so my undergrad is from physics department, and I really like one physicist called Richard Feynman, and he has a sentence that I always carried with my in my research journey, and I would like to share that, which is like, what I cannot create, I do not understand. So that's basically how I try to doing research. I first understand it by creating it, and then improve it. So that'll be my kind of suggestions to the researchers. Yeah,
it's pretty much, if you cannot code it up, you didn't understand it, right?
Yeah, exactly.
Nice. Well, that's great advice, and I think it also like transitions well into the announcement as well for our next guest, who does quite a lot of like understanding of different forms of these methodologies. And so his name is Martin Nebelong. He is a Danish artist, and he will be on the show with us next week too. And so he definitely, more so than anyone, I feel like, is always tinkering with and understanding and pushing the boundaries of what these methodologies can do. But yeah, no, thank you again, Ruilong. I truly appreciate the time that you've given us.
Thank you for having me.
Thank you very much. It was so much fun, and I mean the discussion could go forever, continue forever. But thank you very much, because you gave us really nice insights into Nerfstudio and how it works, and how you guys decide what to take in and what the agenda is. And I feel there's a lot of exciting new code coming in, and we will have new applications with it.
Yeah, if you are thinking about taking out a PR for Nerfstudio, or thinking about contributing, definitely go ahead and give it a try. Nerfstudio is Apache 2.0 license, so it's commercially permissible, and yeah, you get to work with people like Ruilong. So definitely just give it a try and see what you can make.
Yeah, come to me and we can talk about it. Yeah.
Cool. Well,
Great.
Thanks so much, everyone.
Thank you.
Thank you.
Thanks. Bye.